we can help improve the variability of the transistor, and we can improve the power. We can help them make it smaller, and ultimately, we can really help them improve their yield, which is super important.
In this episode of Embedded Insiders, Scot Bibaud, President and CEO of Atomera, explores the rising cost of semiconductor manufacturing and the challenges of scaling to advanced nodes like 3nm and 2nm. He breaks down the diminishing performance gains and the complexity of high-volume semiconductor architectures. Next, Rich and Scot Morrison, Vice President of Shift-Left Software Product Management at Siemens EDA, discuss the growing specialization of chip design and why development tools must evolve to keep up. But first, Rich and I examine Moore's Law and whether the push for ever smaller chips is truly the best path forward.
Good morning. Welcome to the Embedded Insiders podcast. My name is Rich Nass. I am the Executive Vice President of Open Systems Media, and I do things for embedded computing design, mostly get in the way. And I'm here with the person whose way I get in the most of, Assistant Managing Editor Tiara Oliver. How are you, Tiara?
I'm good. And just to preface, you do not get in the way.
Well, thank you. I do appreciate that. I was hoping you were going to say that. Okay. So what's going on this week? What's the latest in your world? And then I'll tell you what's going on in my world.
Well, I did some interviews, or I did an interview a few weeks ago, and I actually noticed today that it aligned with an interview you recently did. And basically, it's about chips getting harder to develop. We're going smaller into smaller nodes, and architectures are getting more complex. And knowing that you've been in this industry longer than I have, I kind of just wanted to pick your brain, and we can talk about both of those interviews together.
Sure. The one I did was Scot Morrison of a division of Siemens. He's a software guy, really. And this is a problem that has been going on as long as semiconductors have been produced. And it just keeps getting harder and harder as the nodes get smaller and the speeds get faster. And it introduces different issues, like as they get smaller, you have to reduce the power so you can actually produce these things on a die. And the tools continue to get better, but they have to keep up. And if they don't keep up, then we won't be able to produce any more semiconductors. But I've been hearing for as long as I've been doing this that we can see the end. We can see the end. Well, we've been seeing the end for forever, and I don't see the end. I just think it will continue to get better. What was your observation?
Pretty similar. It was also talking about like the tools that we're using to make these new nodes and how those are also getting so expensive, especially for companies that are producing at such high volumes. It's like tough to sustain how expensive the equipment is to even get to the chip size that you need.
Yeah, that is very true. The expense is off the charts. And again, I feel like we've been having this discussion for many, many years. The number of people who can actually produce an ASIC is getting smaller and smaller because the cost of it is just getting ridiculous, into the millions of dollars to produce an ASIC. And that's where the programmable parts come in, where you can actually do some almost as good as an ASIC with a programmable logic part, and in some cases just as good, depending on what your application is.
Mm-hmm. I didn't think about that perspective. Is programmable kind of another solution to maybe not scaling down as much? Maybe we stop at a certain size and just use programmable solutions?
Yeah, that is definitely the case. And some of these die are pretty small. And in most cases, you have to use is it good enough? There's definitely applications where it's not good enough, but for the majority of them, it is. And that actually leads me into an interview that I'm working on where we're going to be talking about reverse engineering. We've been doing some level of reverse engineering for years here at Embedded Computing Design by doing teardowns, but there's people who actually do it to a much more degree, a higher degree than we do. So I'll be talking to somebody at EM Proof, and that's their business where they reverse engineer stuff. And in a lot of cases, people pay them to reverse engineer stuff. In some cases, to see what competitors are doing, but also to see what people are doing with their own products to make sure that they're not hackable, which is really interesting. So I'm really looking forward to doing that interview, which will be aired probably next week by the time you're hearing this podcast.
Awesome. I feel like reverse engineering is definitely something I hear very little about, but also something that probably reaps so much reward and information. So very interesting.
Yeah, it's a lot of fun when we do it here ourselves. Obviously, we don't get into it to the level of using very sophisticated tools. Usually, when I do it, it's just rip it apart, take a hammer to it, take it apart, and then ask lots of questions. And it's always funny when you ask a question, well, why didn't you do this instead of that? And the answer is, well, because we didn't think of that. And then a few years later or a few months later, you see a next generation that it incorporates some of the things that we had talked about in that interview.
Definitely. Well, I think it'll be very helpful for the audience to take a listen to these next few interviews, listening to the challenges of chip development from the experts. We touched on it a little bit, but I know I heard a lot of good information, and I'm sure you did as well. I didn't want to get too into it to spoil it for everyone. So
Yep, absolutely.
Now, here's Scot Bibaud, President and CEO of Atomera.
Yeah, my name is Scot Bibaud. I am the CEO and President of Atomera, which is a materials technology licensing company. And yeah, it might be instructive to give you a little of my background. So I was an engineer a long, long time ago, but have been working in the semiconductor industry, running businesses since the early 90s. Ultimately, I was running a division of Broadcom for many years, and then moved over and ran a division of Altera also for many years. And one thing during my time in semiconductors in the early 90s, we used to bring out new semiconductor nodes every couple of years. And when we did, we were getting 20 or 30% performance improvement on power and on performance with the devices. And that continued all through the 90s and into the 2000s. But in about 2012, we hit the 28 nanometer node in semiconductors. And what I was noticing is that in our businesses, we were struggling to continue to get the power and cost advances that we had gotten before. And I noticed this happening more and more in all of our semiconductor businesses. I was on the executive staff at Broadcom for many years and at Altera, and we were talking about the same issue, which is that many of the semiconductors in the older nodes were not getting the performance boosts that they needed. And in the newer nodes, they were struggling to continue to get 20 to 25% performance boosts going forward. So in 2014, I went to a venture firm, and I started looking into this and a few other problems in the semiconductor industry. And in 2015, I found a company that at the time was called Mears Technologies that made a material that helped to solve this problem. And I joined the company, took it public in 2016 so we could raise money to develop the technology and start to roll out with customers. And so I've been, in 2016, when we went public, we renamed the company Atomera and have been making good progress on bringing this out to the industry ever since.
amazing. Sounds like great work you've been doing. I was wondering if you can provide just a bit more information about what you were talking about, with our semiconductor chips and, getting more expensive at the advanced nodes. I was wondering, how did we get here? And if, in your opinion, can you provide like why you think that the semiconductor manufacturing costs have risen so rapidly at these advanced nodes?
Yeah, it's a great question, and it's important because in the industry, we've always lived with something we call Moore's law. It's not really a law, but it's an expectation that in every 2 or 3 years, we're going to get to 20-25% performance improvement on each new node of semiconductors. Um, and back in the early days, we would sell a wafer for $500 to $1,000, and then the cost would go down as we were manufacturing. We'd bring out a new node, and then we'd start selling that at the high end of 500 to 2,000. It would go down, then we'd introduce a new node, and it kind of went on like that. But these days, it's taking much longer to bring out a new node, so it's no longer 2 years. It's definitely 3 or more years. And the technology required to make those new nodes has become dramatically more expensive. So a few of the things driving that, of course, when we got to the 5 nanometer node a few years back, it really became pretty much mandatory to use EUV lithography tools, which are the most advanced lithography tools that have ever been made and cost between 100 and $200 million for each tool. And you can imagine if you have a high volume production line, you have to buy a bunch of these tools to be able to sustain throughput. So that is quite expensive. The plants just to have to house these pieces of equipment and the advanced filtration and technology that you need just to have those plants costs about $10 to $20 billion to build these days. And those costs are bad, they're very high, but the reason for it is that the architecture of semiconductors, in order to keep trying to move this performance forward so quickly, has really become much more complex. Today, we're making something called a gate-all-around transistor, and it's very, very hard to build it, requiring really, really advanced high-precision tools. And for that reason, it's been speculated that TSMC is charging about $18,000 a wafer today for a 3 nanometer wafer. And the projection is that when we get to 2 nanometers, which is coming soon, that the wafer cost will go up to $30,000 a wafer, which is just hard to believe compared to where we were back, 15 years ago.
I kind of want to jump around with my questions here. Since you mentioned going to 2 nanometer, what do you think are the specific outcomes or impacts when scaling to smaller nodes like 3 or 2 nanometer? And, I know you touched on it a bit, but if there's any more significance in this for the industry.
Yeah. Um, you know, Everything becomes much more complicated when you getting to 3 or 2 nanometer. Of course, I'm sure everybody
Mhm.
understands that. But there's a few things that become really critical. At that geometry, the physics of everything works a little bit differently. Um, and it traditionally in the semiconductor industry, it's been very hard to control leakage power when we got down to smaller process nodes. And you can kind of think of that as the source and drain of the transistor get closer together. It becomes easier for electrons to leak from one to the other. And that is just a power drain that wastes energy. And it's something the industry has spent a lot of time trying to correct. And also, one of the big challenges in semiconductors is something called variability. So if you imagine that we're building a wafer with billions of transistors on it, what you'd like to do is to be absolutely certain that every single transistor is exactly the same. But that's hard to do. The variability between one transistor and another is something that we measure, and we try to keep as close as possible. But if we can't be close, so let's say there's a 10% variability difference between transistors, what you have to do is make each transistor as big as the worst case variability. So you can imagine a billion transistors, if you had to make each one 10% larger to take into account this variability problem, it really means that the size of the die is getting bigger than it has to be. And so those are a couple things that we're really focused on, trying to improve variability and trying to manage that power. And this is all happening in a kind of new architecture called gate-all-around that's very complex with stacked sheets. And so what we see in the industry is that people are turning to material solutions to help solve that. And, and that's what Atomera is all about. In the past, when people were expecting that every couple of years they're going to get a 20 to 25% performance improvement, then they used to say, okay, well, we're not going to do any, like, for example, material innovation or any big architectural changes unless they bring us at least a 20 or 25% performance improvement, because they knew that a new node was coming around the corner, and why bother, right? That was always the hurdle. If you're going to do something new in your manufacturing process, it had to deliver to 20 to 25% performance improvement. And that's why, we talk about at Atomera bad math. That people still think that way. But today, when you're looking at the very, very high cost to get these new wafers, if you can bring just a 5 or a 10% performance improvement, it is a dramatic, a huge cost savings that makes it worthwhile to do. So that's true for PPAC on the economic side, as you talked about. On the technical side, I talked about variability. How can we improve variability? How can we get around some of the big bottlenecks that we're seeing right now, like SRAM not scaling as fast as it could, the slowdown in transistor density, the power performance per watt. So those are all things that we have to get around in the semiconductor manufacturing process to try to get to the level of performance improvements we've seen in the past.
So how is Atomera leveraging, its technology to address these rising costs and the slowing improvements?
Yeah, so Atomera makes a technology, a material that's called MST. Interestingly, MST isn't just like a material that we discovered out in the, in nature somewhere. It is a material that was designed by computer simulations a long time ago, actually, maybe 15 years ago. And we've been working very hard to not only perfect the material itself, but perfect the way that we can deposit it and the things that it does. So we always call MST a toolkit because you can use it to do many different things in the manufacturing process to solve some of the problems I talked about earlier. So if you imagine these gate-all-around transistors that I talked about, they're very complicated, right? If you saw a picture of it, there's just all these layers and interconnects, and wherever there are two different layers or interconnects touching each other, there's it's very important when you're manufacturing it that you can do that as precisely as possible. And the tricky thing when you're making a semiconductor is you do all that very precisely, but then you go to the next step in the process, which might require high heat or some chemical that can impact the prior process. So, for example, you're making a source drain structure and you dope it with phosphorus. So you're putting a lot of phosphorus in there so you can get a lot of extra electrons to be able to get good current flow. And then right at the edge of that source or drain with the high phosphorus, you want to have another region with no phosphorus at all. But then you go to the next step in the manufacturing process and you have to heat up the semiconductor to some very high temperature, and the phosphorus diffuses. It's like brownie in motion. It wants to go where it wants to even out its density to the lower density part of the semiconductor. So one of the things our materials can do is it can kind of put up a fence between that region with the high phosphorus and the region with the lower phosphorus or with no phosphorus, and prevent it, at least slow down its ability to go into that other area. And by doing that, we can help improve the variability of the transistor, and we can improve the power. We can help them make it smaller, and ultimately, we can really help them improve their yield, which is super important. I mean, just thinking about this question of yield, imagine you have we were talking about wafers that cost $18,000 to $30,000 per wafer. So if you can improve the yield, and by the way, today in manufacturing, they're running at much lower yields than historically they have because it's just very hard to make. So if you can improve the yield by 1%, you're getting a value of about, let's say, $200 per wafer. So you can imagine that it should be worth a lot to put this piece of material in, but they can actually deposit our materials for a tiny fraction of that value.
So I kind of wanted to get more information about these advanced materials. Firstly, like what are the biggest challenges that you guys face in like integrating new materials into existing fabs, and how does Atomera, accomplish that or overcome them?
Yeah, so first of all, let me describe the material a little bit. It's quite interesting. What we do to make our material is we deposit it using a tool that all advanced semiconductor fabs have, called an epitaxial deposition tool. And what epi means is that you take a crystal structure like a semiconductor and you build it up one atomic layer at a time. So you're building on a perfect crystal structure, you put another layer of perfect crystal, and you keep doing that. So you have this lovely, nice crystal lattice that you're growing. We deposit some oxygen, a very small amount of oxygen, not enough to create an oxide, but just enough to kind of bend those perfect crystal lattices. And then we grow more silicon on top, and then we put a little more oxygen to bend the lattice. And we do this making layers of the lattices, and then we add a cap of semiconductors of silicon on top. And so this material we've made has all these really nifty characteristics, and we can incorporate it into the manufacturing process to provide some of those improvements we talked about earlier, like improving variability and a number of other things for these advanced nodes. That, I don't know how it sounds to you, but for someone who doesn't really do this very often, you would think, wow, that sounds really expensive. You're growing these
Yeah.
perfect crystal lattices, you're putting a tiny puff of oxygen. I mean, we really need, it's very hard to build this. You have to keep the oxygen kind of spread far enough apart that it doesn't, if it creates an oxide, it destroys the semiconductor, right? So yeah, it's tricky. But today, in these advanced devices like gate-all-around transistors, in the old days, they used to build transistors primarily with lithography devices. And I talked earlier about a tool called the EUV tool, which is a lithography step, where they're basically painting a pattern on the wafer and then etching out parts of the pattern and depositing other materials in the other pattern. But today, the manufacturing process is using a lot more epi steps, so this epitaxial deposition, than lithography. And once you're using epi, if you wanted to add our new material in there, it's a very minor addition to put our MST into the epi steps. So it's very inexpensive to add that technology and straightforward. So, that's one of the things that we do in our company is we show manufacturers how to deposit our film, and we also show them how to integrate it into the transistor so they get the absolute highest performance or the lowest power consumption or whatever they're trying to accomplish by using MST. In every case, of course, it has to be bringing economic advantage to our customers, or else they won't do it.
So speaking of MST and showing Atomera showing other manufacturers how to use it, how quickly do you anticipate this will be adopted at scale, and how will it impact, or what will be the impact on the more advanced nodes?
Yeah, so we're working with our first customer to take this to volume production. They've actually let us use their name. Most of our customers are pretty secretive, but ST Micro has
Oh,
announced that
wow.
they're working with our technology, and if all goes well, we'll go to production with them in a older process node for power transistors. But in the most advanced nodes, in the past few years, we've really started to get some significant traction. And when I say advanced nodes, I mean not only like this gate-all-around type of architecture I've been talking about, but also in the memory architectures like DRAM. When you're working with companies that are working on the advanced nodes, they have huge teams of engineers that are focused on this. So
Mhm.
as they start to recognize the benefit of MST and where they can implement it, they get very, very interested in it and start running experiments. And of course, the development of a new process node is very, very complex. And these days, I'd say it takes 2 to 3 years. But we've been working with a number of these companies for some time. So we believe that our MST will start to be incorporated very soon into these advanced nodes and memories and go to volume production in the near future.
So, as the industry is moving forward with these advanced materials, do you foresee a future where silicon is entirely replaced, or do you believe it will remain the core foundation of chip manufacturing?
Yeah, that's something people are really interested in. I think, personally, I think it will remain the foundation for a very long time.
Mhm.
As long as I've been in the semiconductor industry, there's been predictions about the point where the physics are no longer allowing you to move to the next step, but they always have found a way to move to the next step, and it's through advanced architectures and advanced materials to enable those architectures. So, there's a few implications to this. It's really, really expensive to come up with these new advanced architectures. And so it really does require kind of an ecosystem of companies around the world who are innovating to bring new technologies to market. We believe that Atomera is going to be a very important one of those. It also means that that the companies have to become, what one of the things that's happening right now is a lot of geopolitics around semiconductors, and there's
Mhm.
been a lot of countries that believe they need to develop their own technology and try to keep that internal. I think there's some really good uh, implications to that, but there's also some challenging ones. And the great implication is that it seems like a lot of regions and countries are recognizing that they need to invest to try to come up with new innovations, and that at the scale of the spending that we need to do this, it has to get some support from the government. On the downside, I hope that it means that international cooperation doesn't get impacted, because ever since I've been in this industry, there has been great cooperation between semiconductor makers all over the world. The only thing I would say, and it really does tie into this last question you had, is
Mhm.
that semiconductors are kind of they have a long life ahead of them.
Yeah.
And there will be other technologies, like right now, gallium nitride is a very big thing that people are talking about. People are talking about quantum computing, which isn't necessarily based on semiconductor materials, but the bulk of the world will continue to rely on semiconductors for electronics going ahead, and electronics are going to need more and more advanced materials. So I think Atomera is paving the way for how a number of new innovative companies will start to enter into the marketplace and enable that future that we all are looking forward to.
Now, here's Rich and Scot Morrison, Vice President of Shift Left Software Product Management at Siemens EDA.
Good afternoon. My name is Rich Nast. I am the Executive Vice President of Open Systems Media. I lead the content team for embedded computing design. My guest this week is Scot Morrison. He is the Vice President of Shift Left Software Product Management at Siemens EDA. He's also an old friend of mine. We go back many, many years, and I won't say how many. Scott, how you doing?
I'm doing fine. And yeah, please don't age us specifically here. But it has been a long time. It's been a while since we talked too, so it's good to talk to you again.
Yeah, absolutely. And I know at Siemens, you guys are doing some very cool things. Back in the day, we were talking a lot about RTOSes. Now we're talking a little bit more about the software components of chip design and IP stuff. And you guys just came out with something pretty significant not too long ago that really helps people in the chip design process. And before I mangle it any further than that, I'd like you to explain what is the problem that needed to be solved here.
Yeah. No, that's good. Well, good place to start, of course, right? Because what we try to do is build solutions for problems that our customers and potential customers are grappling with within the marketplace. And as you said, we've talked about RTOSes and embedded Linux and embedded topics in the past. That's kind of been the bulk of my career. But what we found at Siemens, we have this hardware-assisted verification group, a significant group, been in the market for many years with emulators and FPGA-based prototyping products. And their customer base, and for our competitors, and I think I can safely say, kind of general challenges within the chip design and verification market have been compounding and increasing over the last few years. A lot of it has to do with complexity, and that's complexity of both the software and then the subsequent complexity of the chips, the SoCs themselves. And we like to say that these chips have become more and more specialized over time. It used to be in the market, people had very kind of generalized processors, and when you were building a system, you would go out and find the thing that was closest. If you had a high volume and a good relationship with a semiconductor company, then you could go and influence their future product direction and get features in there, but the chips still tend to be very specialized. But if you look in multiple markets these days, automotive is a great example, aerospace, hyperscalers are developing their own chips, for search and training and for inference and things like that. It's a lot of custom chip development in the market. And so these chips are really software defined. They're defined by what they're supposed to do and the software workloads that they're supposed to run. And those workloads are getting very, very complicated, for autonomous driving and for ADAS, if we talk about automotive, for generative AI, if we're talking about cloud-based applications. So very, very complex software workloads are leading to very, very complex chips.
So let me interrupt you there because I want to understand the difference between these different processors. Are they really that different based on the application? Does it make that big a difference from what you're trying to achieve?
It does. I mean, it depends on what specific application you're talking about, right? If you're talking about autonomous driving, then obviously you're talking about a safety critical application. So you have to have mixed safety criticality implementations there. If you're talking about something like search or inferencing, then those are highly specialized chips. They tend to have, much larger numbers for inference, for instance, of smaller cores. So, it's not just about adding additional cores within a completely classical type of architecture for a chip. There really is a very strong influence of how they're doing. That being said, it's all building from the same building blocks, right? That people have today. Maybe some very specialized NPUs or something like that, but the chips themselves, the architectures, yes, depending on the application, the chips are being laid out in a very application-specific way for the software use case, which is really interesting. It's kind of a golden age for chip design right now. It's it's a lot more designs in process, a lot more customization, a lot more complexity, like I said. So, I think there have been times in our history of this market where, it was all about just trying to crank up the clock a little bit more. And then the multi-core thing came along, and 2 to 4 to 8 to 16 cores and how they interconnect. But it was all around SMP workloads and kind of, very, when I think in terms of today's workloads, kind of simple approaches. Now it's the sky's the limit, and we're seeing a lot of variability in terms of software workloads and therefore chip architectures. So it's become, even more interesting in many ways and more challenging than it has been for a long time. And the costs have been going up like crazy around these things, right? As the gate counts go up, and you see multi-billion and then 10 billion and 20 billion gates, and it's the old kind of more sequential development and verification processes have broken down. We had one of the biggest semiconductor companies in the world come to our planning meeting last year and say that they are dealing with a significant increase in the errata for their chips and the associated firmware, up to 3.5 times what it used to be. And it's all around complexity, they said. Using simplified workloads during the early development process leaves issues uncovered. And they said that the approach that they are going to adopt, kind of the core of their strategy in the future, is shifting realistic software workloads as early as possible into the chip development process to uncover these issues early and get the errata under control.
Okay, the errata. Let's talk about that a little bit. Is that something that hadn't been an issue before but is now?
Certainly the increase. I mean, there's always been errata in these chips, right? Things that they find post-release. And usually what happens if there's hardware errata is they work around it in the software, and that works pretty well. Now they're dealing with kind of an increase in the amount of hardware errata. It can certainly push out the timeframes, of adoption in particular, maybe not release, but certainly adoption, when you have to deal with these issues through software. And just the associated firmware. The firmware, because the chips are so much more complicated, the firmware is more complicated. And, they've had to really up-level their software development and testing infrastructure and capabilities. And so just keeping that under control. So, RAD has always been around, both hardware and software, but complexity has just made it so much more difficult, and if you want to keep your chip development timeframes under control and not have those move endlessly to the right, and the, kind of absolute amount or number of errata that you're releasing with, then, what you have to do is, up-level multiple development processes. But in particular, what we're hearing in the industry is shift left realistic software workloads. That's the best way to identify issues early.
Okay, but never fear, because you guys have some automated process. You hit a button and all this stuff just happens for you, right?
We certainly have solutions that we are offering to the market, and we did have a major release a month ago. We announced a whole new product suite called the Nexus products, which is kind of a complementary brand to the Veloce emulator and FPGA-based prototyping products that we've offered for many, many years. Some of the products in the Nexus suite are kind of updated versions, and we also had some brand new products in there. I think, rather than getting into the details of all of those, we're obviously happy to follow up with anybody on that, but sticking to kind of the general problems that we just kind of scoped or defined, the solutions, which you're asking about, is really to have a connected development flow. So if you look in terms of these very, very complex software workloads, it's very easy to say, well, let's just use more complicated workloads during the chip development process. And if you're starting at kind of an emulator, emulators are very high speed compared to software-based RTL simulators, but still to take a very large software workload, like a complicated Linux or a full Android, it can take literally tens of hours to just boot such a software workload on an emulator. That's not a very rapid, development cycle if somebody wants to use a realistic workload. So it's really not that feasible to do. There are cases where you can go through that boot process and you can capture checkpoints, and then you can do development from there, and that works very well, unless you have to make changes, and then you have to go back and rebuild, which is also a long process, and reboot, and you can take a day or multiple days to do that. That's not very effective. And so within the market for a while, people have been using virtual platforms. Sometimes they do early development, or maybe just early software development, or maybe they can even do some configuration scenario trade-offs on virtual platforms, and that's useful. They're not nearly as accurate as an emulator is going to be. An emulator is cycle accurate. So if you really want to analyze the performance, and just as importantly, maybe more importantly, depending on the application, the power of the chip, power consumption, and power utilization, you're going to need an emulator. But really, it's kind of to take the best of both of those worlds, right? The speed of a virtual platform and the accuracy of an emulator, and develop a connected flow where people can start very early on, even before they do any RTL development or they source any RTL components from their suppliers, put together a representative model of the SoC or SoC concepts that they have for trade-off purposes, build that, bring up realistic software workloads on it, and be able to execute those, from the very start, from the earliest phases of their development process, and then be able to seamlessly migrate those software workloads all the way to an emulator. And there's a really interesting middle step here that, not everybody supports and not everybody does, but we had a speaker at our launch come in and talk about how they've been using a hybrid strategy from us for years, which we also up-leveled significantly as part of this launch. Previously called HiCon, but now Nexus Hybrid. And what that allows people to do is have certain components of the chip running on a virtual platform at high speed but less accuracy, and then have other components running in an emulator, at a much more accurate but therefore slower speed, and tie those together seamlessly so it looks like a single chip, and from a simulation standpoint, and you can boot a workload. The workload is, completely unaware the fact that it's a hybrid model, and be able to bring both those things together and boot very, very quickly. For instance, you can bring up the largest software workloads in, kind of maximum 10 minutes because you booted on the virtual side, and then be able to either have other components, maybe a GPU or an NPU or peripherals that are in the emulator, and you focus on those and cycle accurate analysis or power analysis. And there's also a capability to even transition, after you do your fast boot, completely into RTL. So you get the best of the virtual world for fast boot, and then you transition over and best of the emulator world for accuracy. So the idea, though, is to have a complete spectrum all the way from virtual to full emulation. This is what the market needs. We have customers that are doing all these different aspects, but now it's a more integrated and connected flow. With example complex software workloads, and complementing the tooling that people have used, which tend to be more kind of hardware and waveform focus, with kind of more classical embedded software development tools as well. So it feels familiar to software developers. If you're going to ask software developers to use this and work on realistic workloads, you need a tooling environment that is familiar to them. And of course, we supply such an environment, but as with anything these days, it's also open, and people can bring along their own tools and whatever they're familiar with, from their suppliers or partners or in-house, and integrate those.
Is there artificial intelligence built into any of this stuff?
There is going to be artificial intelligence built into this flow. I mean, there's things underway. It'd be a good follow-on discussion. To help people through the process, because anytime you have complexity, anytime that you have an engineering development process where somebody with significant expertise would help the process, that's a perfect application area to bring in trained AI assistants. And so we are developing and will be introducing AI capabilities to help people through this flow. What we have done as of last month is released a completely end-to-end integrated full spectrum development flow. Yes, AI needs to be part of that, and there are things in development right now to enable that.
So we're back to just hit a button and it just does it all for you, right?
Well, hit a button and get a lot of guidance. And yes, certain things will be automated. Maybe not the first step, but kind of interim and long term. I mean, and we have that, if we get back to Siemens for a second, for some of our other EDA related tools, there's an ever increasing level of functionality around AI and ML assistance and things like that. That is the future, let's face it. It doesn't take the engineer completely out of the loop, but it certainly makes them much, much more productive. And that's a vision kind of across the board. And you will see that in this full spectrum development flow in the future.
Yeah, I'm trying to get the vision of where we want to get to. And it's a little bit cloudy. We're taking these steps to get there, and I'm trying to vision what there actually is. If you know what I mean. The applications are becoming so complex. And is it like we were designing a few years ago, where there is some level of intelligence that will help you get there, but it is there, and I'm doing air quotes around there, an unachievable endpoint?
Well, I think with anything, in terms of automation in any industry, but from a technical engineering perspective, every time you bring along tools that allow people to automate or simplify any development step, what it really enables them to do is focus their energies in other areas, in many ways in more productive areas, kind of value adds and things like that. So it's I strongly believe that will always be the case. AI is somewhat unique, but on the other hand, I think it's an evolutionary step in terms of the assistance to the designer or the developer. And when we automate or simplify many of the tasks people have to do, it just frees them to do in many ways more creative things. And that's exciting to all of us, right? Nobody likes to do the mundane work, right? It's all about the creation aspects of it. So where there is exactly, to follow along with your air quotes, it's up and up in terms of the summit, but I don't think you ever reach the peak, right? Things get more and more automated, but they get more complicated as well. You need that automation. The things that people are doing today were really not feasible if you go back 10 or 20 years in terms of the underlying tools that were available to people. But now they are feasible. And boy, if I had a crystal ball and could say in 10 years from now what people are going to be doing with all of this, that would be wonderful, and I'd probably be rich at that point in time. But it's upwards. I can tell you it's upwards, and it's to more complexity and features that we can't even dream about right now. And that's what we're here to do. We're an underlying kind of technology supply company. We want to always, up the value and the capabilities of our products as does everyone in the market, to enable people to go faster and do things that are more performant and better than they were in the past. And it's always exciting for us to see what people do with this.
And you're trying to help them get there, right?
We will help them get there.
Very good. To wrap this up, how do people get more information about all the stuff we just talked about?
Yes, they can come to the Siemens website if they just do a search in their browser and search engine of choice for Innexis, INNEXIS, and Siemens. They'll drop in some landing pages, and they can or follow up with their Siemens sales rep, and
Awesome.
we'd be happy to talk to them.
Thank you very much, Scott. I appreciate you taking the time and dumbing this down for me so I could understand it.
Well, don't be too modest, Rich, but yes, it's a challenge to get this in 10 minutes, but I think we did it.
Absolutely. That was Scot Morrison. He is the Vice President of Shift Left Software Product Management at Siemens EDA, and I am Rich Nass with Open Systems Media.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.